So then of course, there are 4 ways in which you can test these materials. We can group them into 4 different ways. One of course is what we can call as physical properties. Second is the mechanical properties. Third is the survivability during construction. And fourth is durability. We are always trying to say properties and characteristics. Mind you this now. Characteristics, what do you mean characteristic actually? We talk of stress and characteristics normally. We talk of a strength value. Isn't it? We are interested in the total behavior. Why this becomes important is, I told you, the fabric, textile fabric, and also the filaments and things are tested by textile people normally. But they are bothered with the ultimate strength. Not even strain also. But for us now, for design for reinforcement, both are important. We need the total thing, we need the modulus. And the tangent modulus, secant modulus, all of them are important for us now. So we always need a total stress and curve. So if you buy the equipment which is used by them, that will not sufficient. The data which they are giving is not sufficient because that is purely for quality control. And also, they would not like to stop the production. So, particularly in the filaments now, it picks up the filament immediately and gives the result also quickly. So that you can change the temperature, whatever you want to change it now. We are not worried about the time of testing, or duration of testing. We want to get the data for our design actually. So these are 2 different ways of looking at it now. So all the testing which they are doing could be right. In the sampling we are going to see it is different actually. So let us see one by one. When you talk of the physical properties now, one important thing is thickness, mass per unit area, opening size. So for a given material we are talking of, it could be a non-woven kind of geotextile, it could be woven geotextile. So these 2, let us say, we are taking for example now. So when you talk of thickness now, why it is important for us? Take a case of a woven geotextile, a non-woven geotextile. Why thickness is important? The characteristics of flow, hydraulic characteristics, are obviously going to depend upon this. Okay, and also in the beginning, this feed of these fibers, particularly staple fibers, was done manually. That means a lump of this like cotton was simply being fed, and then of course process of punching was happening. So when you look at that now, you look at blanket also, the old blankets, cotton blankets, you find that the cotton has moved to one place and only the outer cover is there. Same thing will happen here also. So along this entire product now, it could be having different thicknesses also. So that speaks to the quality. So here also we are going to do number of tests to assess the behavior, to assess the quality of the entire material. So thickness is going to give us that, and coupled with the mass per unit area, naturally these are parallel to each other one way. So it should be same throughout the length and breadth of the roll actually. So here also is a parameter which is a simple one to measure. You define the size and shape, just weigh it. And even here also we are going to think of this, but these measurements, however simple they are, particularly the mass per unit area, is measured automatically by a machine, by weighing machine and recorded there. I can't put values, feed it. The machine is automatically recording and then giving you the output actually in an average fashion, things like that now. So the output is going to be computerized actually. Otherwise, we can manipulate. So that manipulation is avoided by completely connecting to the systems, online systems. So now, if the mass per unit area is more for a given kind of material, what does it mean actually? Usually for a given kind of product now, it is a better material. As the mass, basic mass is increasing, it is bound to be a better and better material. If thickness is more and all, I can't say anything. We are talking of a quality of thickness only. Thickness by itself may not be anything, but if it is very thick, naturally, it has got a different characteristic rather than being very thin actually. So these 2 will be obviously simple parameters, but tell a lot for those who are experienced in this. Okay, we will talk more on this later. What about the opening size? Opening size is something like our particle size now. So we will talk of effective opening size today and how it reflects. You can say something like D10, something like D60. So it tells us, normal D10 will give us some idea of the soil which we are going to think of. Same thing here, there is some apparent opening size we will define clearly. So actually these 3 are some of the most important characteristics, and exactly like our liquid plastic limit, they will tell you all about it. We may not use in direct design also. We may use only the OAS but then we actually measure the tomorrow permeability, both planar and perpendicular flow. Okay, we use it actually as specification, but we also want to measure the hydraulic characteristics of that later. So these are something simple like our classification soils and very useful, but may or may not be necessarily part of specification. It could be also, but then the final quality depends upon the parameters you are going to pick up now. Then of course, the roll width, roll length, roll weight, to carry it, transport it, go down, to cover it, naturally this is important. Now it can be carried by human labor, or what kind of machines, cranes you are going to have, what kind of go down we are going to have because it is stored properly. So this is going to be important actually, otherwise it doesn't have anything. And the seaming and all are going to come later. So that is the basis of it. Then there is another kind of testing which you look at, which is called index testing. The issue of course which you are going to have is, we got such large widths and large lengths basically. Now if you take a sample, how small you should take, how big you should take? Very difficult. So for example, if you look at the strength part of it now, the tester engineers are used to using widths and lengths of in inches, 3 inches, 2 inches like that now. So 3 inches long and 1 inch wide. 1 inch means 25 millimeters, 3 means 75 millimeters roughly. So they were used to doing tests on very small size specimen now, and those days probably the width of the roll also was less. But now that we are using very large widths now, so testing small pieces like this may not be effective. And also they were doing the testing at very high speed of testing. I told you quality in the production is very important. So the test itself was done at the rate of 300 millimeter per minute. Is there a test actually in civil engineering which we do at 300 per minute? No? No. Have you done any bitumen testing any time? In mixed design, Marshall test, computer test is done actually at the speed. No other test we do at the speed. Okay, we also specify the kind of machine, not that I am going to use a Marshall machine for this now. The point is that we do not do normal testing at the kind of speed. So they have done it for their quality control only, but here we want to know our loads are not so fast. We are talking of either static loading or of course seismic loading. Okay, so our designs are done based upon static loading only. So this kind of speed of testing and this kind of sample size is not going to be sufficient, adequate for this purpose. But then what is the big size? It's good if I test the whole width, 5.5 meters. If the capacity of this is, let's say, 100 kilometers per meter now, how big machines I am going to have? So in concept now, it's very easy for me to think that I will have a full specimen, very huge specimen, and you know what kind of grip I am going to have. I am going to test a sample like this, a specimen like this. It's a cloth, it's not a rigid piece, it's a cloth, it will be wavy. And then the grip has to be perfectly parallel. And then this entire thing will be actually loaded, I mean compression or tension. So it will be under torsion also. So if you really go there, it's not as easy as you think now. It has to be really linear axial, it has to be really perpendicular, and the specimen and the grip actually has to be parallel to both things now. This is typically a specimen actually, we will see this is a parallel specimen also. So the point we are going to make is now, we need wider widths now. So a lot of work has been done actually by Bernard and Miles long back, who were earlier in ICI. Miles has come also to India once. So the point we are trying to make is now, if you have 1 meter width, it's very good. So they went on doing different sample widths and sample lengths and different speeds now. Obviously one thing is very clear, that the faster rate of loading, it gives you very high strength. This is true with all materials, it's also true with soil. But with the range of loads we are going to have, it does not affect us. But in the case of synthetics now, obviously it affects a lot. So we have to fix a speed much lower than that, number one. And then we also have to fix a width in such a way that we can at least test it commonly. Otherwise, 200 kilonewton per meter now, if you take meter width now, the capacity of the machine should be much more than that basically. Accuracy should be much more. So this problem is going to come because of all of them now, they came to some understanding now, Bhaiya, I can't test the whole width now, I will come to somewhere in between now. More than the textile specifications and less than what we all would want it actually. So this is called index testing now. Okay, so that means it's not a true value, but then we are using in design. That value we are going to use in design. So that is something which you are going to keep in mind. And then certain tests you do only for design anyway. One is we wanted to full-fledged testing and we wanted to maybe use for quality control. Some of them we are doing for design anyway. Modification of that, it could be same also. Sometimes same, but sometimes not really same. And then also, famous thing is that in isolation. For example, we talk of hydraulic parameters now. I can have this geotextile and then have some loading on that and allow flow of water along or across. Okay, where is the soil here now? There is no soil. Just only geotextile is used for testing. So actually I forgot that name, Professor Alan McGowan. He is the first one to do a testing on the subject of compressibility of geotextiles. He is from Chattisgargh University, one of the major inventors of this technology, but he is not very popular. Like me, he is notorious also. But he has done classic work actually. So that work relates to what is the effect of confinement on this now. That means if you are doing a tension testing also, if you are compressing on both sides as at the in situ stresses, what is the kind of variation we are going to get now? Okay, effect of confinement has to be definitely done, taken into consideration in the case of hydraulic properties. So that is really confined testing. So we have now two kinds of testing for hydraulic properties. One is in isolation, that means there is no soil there at the top and bottom, and under confinement really means that we are going to have the soil of the kind which we are going to have we are going to use it, or it may be standard also. Now there is a problem for me. Our Mohan wants actually friction value now. There is friction now. So am I going to use a standard kind of sand like a little bit sand in compressive testing of cement? Or I am going to bring that soil from the field and then start using it. So this query is always going to be there. Okay, so confinement really means actual site condition or a standard condition imposed by the testing authorities or specification. So that is something is there. Finally, yes, we are doing a lot of testing like this, but then the full scale testing is not possible. So we call it prototype testing. We are talking of walls now, could be 35 meter, could be 40, 50, 60 slopes also. We can't do all the testing now. I take a model, but not model like I started with 6 centimeters, a model of meters, 5 meters, 10 meters. This is called prototype. Also indirectly it will be centrifuge testing also, wherein we get the information on not only the overall behavior, but the individual component behavior. Like in our case now, we are interested in finding out the connection strength, connection load between the reinforcement and the fascia. Naturally, we need to do special kind of testing. Okay, and also when we develop what is real movement, displacement in the member now, naturally we need a specialized testing. So that will be not part of a routine work, not for a designer now, but to advance understanding on this now, to develop better procedures for design, naturally that becomes very relevant now. So you see this now, initially we started saying that the field people, designers need some kind of testing. The quality control people need something during manufacture and during construction. And then the design people have some other data, and then we will also see actually step by step other kinds of things now. What are other things now? The tensile strength characteristics now. So the first kind of testing we thought of from strength viewpoint was imitate what the rest of people do it. So they were doing a narrow strip. So we have a narrow strip testing, strength testing, narrow strip tensile strength testing for geotextiles. And all the research done by Bernard and Miles, ICA, long back, has revealed that we will test now a smaller width like 200 millimeters. We will talk other dimensions now. So, but 1 meter gives us perfect value. We can't do all that now. Now, why we actually want larger size? Statistically, you do know? You take a case of a rock, let us say, about which you are familiar with. Why should you take a larger dimension piece of rock, intact rock, or should you take a smaller piece? Which one is likely to have more strength? In any area only. Any idea? If you take a smaller piece of material, it is less likely to have defects actually. If you take larger pieces, it is going to have the micro fractures, mini fractures, and even much larger one will have folds and falls. Everything is going to be there in the larger the dimension of the specimen. If you make a smaller specimen, basically, it is going to be strongest actually, because only microfishes are going to be there. Whereas in other ones, there macro also are there. Joints could be there. So that's why when you take a larger sample, naturally, we have more possible damage, more weakness coming out actually. So the smaller you take now, it's always going to be better actually statistically also. So we prefer larger one, but today we are using a 200 millimeter width as a standard width for all the testing. So that is what we call as wide width tensile testing. Narrow and wide. We'll get more details later. Then of course we have to find out what is the behavior with respect to time. We know plastics are going to be highly susceptible to creep, and creep will vary from is a temperature function. So all this is going to be something. Junction. The joint, I said, the node we said actually, where the transfer of load is going to occur at macro level is going to be very important. We don't normally seam for loading, for strengthening, for reinforcement purposes, but sometimes when I'm doing for drainage now, we will be forced to seam also. It could be longitudinal, it could be also lateral. So this also we have to do some testing. So it's not very common, but then it's required to be done now, because seam is going to be the weakest portion of any structure. So that will be the tensile strength now. From engineering viewpoint now, we also require friction. We'll talk more on that later now, because through friction only the load is coming on the member as tension. So when once you talk of friction now, what kind of friction now? There is one case wherein you keep the geosynthetic inert and then have the soil moving over that in a box, direct shear box. So some people say, no, it's not effective. In the field, it's not like that now. So what you do, you have a box now, put the soil and put the geosynthetic, over there put more soil, apply the load in a similar way like a direct shear, and then pull it out, such that the soil is there on both sides. Okay, that is what we call as pull-out test. So we will find that there will be use for both of them. Actual system, they will have use for both of them. So these values will be definitely linked to our angle of shear resistance in normal soils. So people don't do this also normally, because they assume a factor from the angle of shear resistance for the soil itself actually. So anyway, this is very easy test to do, and then only for very large projects we have to do it. Then I've got inclined plane. I also shown you a sample of GCL, geosynthetic clay liner, wherein bentonite is there. When bentonite is there, we know very well its angle of friction is going to be very, very small. So we can't use this or direct shear or anything else now. We go back to physics now. We have an inclined plane, keep the material there and keep increasing the slope of that. So the moment it is going to fall down, that is the angle of friction. We'll see that also. So that is for angles which are definitely of the order of 5 degrees, in which we can do a conventional soil-like testing. So that is for friction now. Then for hydraulic characteristics, we are going to think of in-plane flow. It's called now transmissivity. That means the actual flow characteristics along that, the drainage characteristics are measured by actually along the plane. And remember this word now, that word is called in non-dimensional form transmissivity. This will be now defined later. It will be non-dimensional form. That means non-dimensional means it doesn't consider the thickness then. Then of course, other direction we are going to use for filtration characteristics usually, and that is really the normal flow, and that definition again divided of thickness is going to be called as permittivity. This is a typical flow characteristic. It's like permittivity coefficient. Okay, permittivity coefficient multiplied by thickness or divided by thickness is going to come out later. We will see that clearly. And then of course, when a flow is occurring, when a huge mass like a dam or something like that along the drains, naturally there is a loss of head during the flow also, because though we are perfectly trying to design it now, there will be some particles getting into this also. So we like to measure what is head loss in the geotextile. The relationship between head loss in the soil, which you already know for a normal perimeter, head loss in the soil in a clay kind of soil now, with respect to head loss within the geotextile is defined. Ratio of these two is called gradient ratio. We will define that more accurately later. So they are called gradient ratio. So again, we are talking of efficacy of this now. Some people say, oh, I don't bother about this, let me actually measure the actual discharge capacity. Good. I take a Proctor kind of sample, soak it, saturate it, and below that could be a geotextile, and keep pouring water, continuously find out what is discharge actually. A lot of interesting results our students have had actually, and the way in which it's measured is very simple, but then it's not as simple as you think, because there is a cake formation happening in the system basically, so the changes are going to be accommodated. So all that will come in the both the long-term flow and the gradient ratio test. So you should remember that now the long-term flow or hydraulic characteristics are going to come out actually in terms of field application now. That means it's a confined test and things may change in course of time. So long-term means maybe 20 days, it's not years. Okay, under the confining conditions, overburden pressure. So we have to measure now under different overburden pressures or apparent confining pressures, and also under the similar soil conditions in this case, because the particles, fine particles which are smaller than the smallest voids will definitely pass through. So near the geotextiles, the actual particle size distribution is likely to change. We will actually see that in measurement and physically also. So that is why these are very critical for us now if we want a drainage function to be satisfied happily. So a lot of work has been done, is being done recently. One of the hot topics actually, that how the people, I have shown you the drainage composite now, what exact discharge capacity is a point of, I don't know, controversy, a lot of discussion, because each company will provide a kind of composite. Now they may claim that the value is going to be high, but actual conditions it's going to be a problem. Even a PVD we are talking of, I have shown a PVD which is just in open system now. We just have a geotextile and we have a central core. But when once it is going to be installed in the soft clay, what is going to happen now? Naturally, soil is going to settle through consolidation. So this will not be vertical now, this will be crooked like me. So when it's crimped actually, naturally the discharge capacity is less now. So apart from the confining pressure we are looking at now, we also see in crimped stage. In fact, I do have done a lot of such testing also, but the standard is different. We made a special equipment to find out the flow characteristics of a PVD under the natural confinement at different crimps also. That means the one is bent actually, buckled, like buckling behavior basically. So all that is going to come critical actually for all hydraulic applications. Then of course, all the three, what were three we considered now for engineering characteristics? We talked of the strength basically, we talked of the friction, we talked of the hydraulic characteristics. Then comes the most important part of it, that we had done all of them perfectly, we got a very good design value, but during installation in the field, because obviously we are going to put stones, aggregates, machines can move over that, and many things can happen now. So there is a possible damage to this now. Somebody may inadvertently throw some stone on that now. I may walk with spiked shoes. Our good friend has gone for a running race and he started walking on the geotextile actually. It may get spiked also. And somebody may put a matchstick also there. So all the possible damages have to be conceived. Whether you are in India or abroad, this is really true. So these are done by tests imitating from the textile literature, combining our normal large soil mechanics, and also using the aggregate testing. So these tests are, that's why suppose you find out the CBR push through. CBR actually is not CBR testing equipment, something like that, but CBR plunger is used in such kind of testing. And instead of CBR plunger, I can have a smaller rod, 8 millimeter rod now. So rod can be pointed or can be sharp. Instead of that, I can have a sphere also. So like this, all of them now, possible damage. Another important thing will be, it's not written here now, tear test. That means somebody inadvertently cuts a small piece. End may. Is it going to propagate or not? Because it's not going to propagate, I am not bothered about it. Now these problems are not necessarily going to come in a rigid kind of geogrid. It may also come in flexible geogrid. They are relevant for geotextiles, but you have to see which kind of grid we are going to use and what possible damage can be there also in, you can say, drainage composites. So all of them, abrasion is going to come probably in railways. There is more abrasion because of ballast actually. And they got a lot of ways now, abrasion test for rock like this, going round and round, or going up and down like this under different pressures. What is the change? I will show you some results also. What change is going to come now. So textile laboratories have it now. We still use the same textile testing systems for understanding the behavior of geotextile also. Tearing, as I said already, topsoil tear now. Cone drop means somebody dumped a stone. Okay, that's a possible damage now. When damage is going to do more actually, based upon the material below. The material below is hard, You put a geotextile over there and put a drop of stone there, the damage is going to be more. But suppose it's on a soft soil. You place this now, dump a stone, nothing will happen because that also will come down actually. So the damage is going to be based upon what is the base on which the geotextile is going to be there. And then also, normally we never load it directly. We always place a soil as a cover and then run the machines, run the rollers over that now. So if the thickness is more of that cover soil, naturally damage is going to be less on this now. If there is no cover, naturally this is a problem now. Obviously we think that we should have a cover. We know machine can go over this and normally we don't walk over that also. Sometimes unavoidable. Otherwise we don't walk over that, definitely not with sharp shoes. Okay? And not with maybe canvas shoes, maybe running shoes. But the point is that damage is going to be implemented on that now. So the kind of construction we are going to have, the kind of labor we are going to have, the kind of surface we are going to have, the kind of cover, all of them are going to mean something now. So this will be indirectly simulated in this, indirectly. Is it not? After all, we got the loss and abrasion test and aggregates. Is it going to occur really in the field? When stones and big balls, steel balls are going to rotate? No. It is a test which is experienced now. And finally, they say that, okay, limit is 30% or 20% based upon whether we're going to use national highways or we're going to use in rural roads now. So same way here also, people specify the values now. These values are purely based on experience and they may get changed over years with more experience comes in now. In the same way, if the cover soil is going to clay, damage is going to be less. If the cover soil is going to be aggregate kind of thing or gravelly, natural damage is going to be more. Like this, we have to imagine. So the factor of damage due to construction will depend upon all these features of construction. Okay, there is no standard value for that. So that is something you have to keep in mind.